In this lecture, we are going to look at interrupts. An interrupt is a hardware signal or a software event that requires the attention of the microprocessor. Hence, the classification of interrupts into hardware and software interrupts. An interrupt causes automatic branching to a sub-program called an interrupt service routine, ISR in short, or interrupt handler. The ISR is specifically designed to handle the condition that caused the interrupt. An ISR is terminated by a special return instruction called an interrupt return instruction. The interrupt return instruction enables branching back to the point at which the program was interrupted. Hardware interrupts are signaled by a voltage signal on an interrupt pin. In level-triggered interrupts, a high or a low signal level on the pin indicates presence of an interrupt. In edge-triggered interrupts, a rising or falling edge on the pin indicates the presence of an interrupt. Let's look at some uses that we can put hardware interrupts to. 1. Control of external hardware and I/O devices so as to respond to them only when some condition happens or when they are read. As an example, we can arrange a keyboard to raise an interrupt whenever a key is pressed on it. The microprocessor then responds to the interrupt and hence the key that has been pressed. 2. Saving critical registers when power is lost. We can have a monitoring circuit generating an alarm whenever power is lost. The microprocessor then responds by saving the critical registers to some battery-backed RAM. 3. Timing applications. We can have a timing circuit generating an interrupt whenever a timeout occurs. The microprocessor then responds accordingly. As an example, it can respond by raising an alarm. Interrupts that are initiated by software events can be classified into exceptions, traps, and software interrupts. Exceptions cause branching to an ISR when an undesirable result or condition occurs during the execution of an instruction. Examples are division by zero error, overflow, attempt to execute an invalid instruction, and attempt to access an invalid memory location. Traps cause branching to an ISR after execution of an instruction or execution of an instruction at some point in the program. Examples are the debug interrupt and the breakpoint interrupt. The debug interrupt causes branching to an ISR after execution of each and every instruction in the program. This enables the programmer to check the results of the execution of each and every instruction. The breakpoint interrupt causes branching to an ISR when a breakpoint is reached. Breakpoints are inserted into the program by the programmer to enable debugging of the program. Software interrupts cause branching to an ISR when an interrupt instruction is executed. Let's zoom in on the 8086 interrupts. There are two types of hardware interrupts. These are the non-maskable interrupt NMI and the maskable interrupt INT-R. The non-maskable interrupt is indicated by a high level or a rising edge on the NMI pin. The maskable interrupt is indicated by a high level on the INT-R pin. The maskable interrupt has an associated interrupt acknowledge pin named INT-A. INT-A is used to indicate to hardware devices that the microprocessor acknowledges receiving the interrupt. Supported exceptions are division error and overflow. Supported traps are debug and breakpoint traps. The 8086 also supports software interrupts through execution of interrupt instructions. The different interrupts in the 8086 are assigned different numbers called type numbers. A type number is an 8-bit number and therefore allows the 8086 to support up to 256 different types of interrupts. Type 0 is the divide error exception. Type 1 is the debug trap. Type 2 is the non-maskable hardware interrupt. Type 3 is the breakpoint trap. Type 4 is the overflow exception. At the time the 8086 was introduced, types 5 to 31 were reserved for future developments in the Intel microprocessors. Types 32 to 255 are used by the int-ara hardware interrupt and the software interrupts. The addresses at which the respective ISRs for the different interrupts start are known as vectors. Each vector consists of a 16-bit segment selector to define the segment that contains the ISR and a 16-bit offset address to define the offset of the starting address of the ISR from the base of the segment. The vectors are stored in a reserved portion of memory called a vector table. The vector table is located at addresses 0000H through to 003FFH. It therefore contains 256 vector entries for the 256 possible interrupt types. The type number is the index of the corresponding vector into the vector table. The address at which the vector is located is equal to the type number multiplied by 4. Let's illustrate how addresses of ISRs are obtained from the vector table. Shown is the vector table and the corresponding vectors. Suppose the type number is 02H. The address at which the corresponding vector is located is given by 02H by 4, which is 08H. The vector occupies addresses 08, 09, 0A, and 0B. 08 and 09 hold the offset of the first instruction in the ISR. 0A and 0B hold the segment selector for the segment that contains the ISR. In this case, the offset of the first instruction in the ISR is 10E0H and the segment selector is 0040H. If the type number is A0H, the address at which the vector is located is given by A0H by 4, which is 280H. Therefore, the offset of the first instruction in the ISR is 8050H and the segment selector is 0100H. Branching to an ISR occurs at instruction boundaries. For hardware interrupts, the current instruction is completed before the branching. For software interrupts, branching occurs soon after the execution of the instruction that raises the interrupt. The sequence of events then followed after the instruction boundary has been reached are: 1. The flag register is pushed onto the stack to preserve it. 2. The code segment register followed by the instruction pointer are pushed onto the stack to preserve them. 3. The interrupt flag is cleared to disable further interrupts. 4. The type number is determined. For non-maskable interrupts, traps, and exceptions, the type number is supplied inherently by the interrupt. For the int-ara, the type number is supplied by the external hardware that raised the interrupt. For software interrupts, the type number is supplied by the instruction. 5. The vector corresponding to the type number is fetched from the vector table. 6th, the vector is loaded into the code segment register and the instruction pointer. This makes instruction execution to branch to the beginning of the interrupt handler. Let's zoom in on how the int R and the software interrupts supply the type numbers. For the int R, the 8086 issues an interrupt acknowledge cycle on the system bus. After receiving the interrupt acknowledge cycle, the interrupting device places the type number on the data bus for the 8086 to read. For software interrupts, the type number is supplied as an operand of the instruction. The things to do inside the interrupt handler are: 1. The CPU registers must be saved so as to preserve their contents for use after return from the interrupt handler. They can be saved by pushing them onto the stack. 2. The procedure for handling the interrupt is run. 3. The CPU registers are restored. If they had been pushed onto the stack, they are popped back in a reverse order. Thus, the structure of the ISR. On entering the ISR, all the general purpose registers are pushed onto the stack, after which the code that defines the ISR is executed. On completion of the ISR code, all the GPRs are popped back, and then an interrupt return instruction is executed to branch back to the point that was interrupted. The interrupt return instruction is a special return instruction that, in addition to popping back the return address from the stack, also pops back the flag register. The instruction is summarized by the two events. 1. The instruction pointer followed by the code segment register are popped back from the stack. 2. The flag register is popped back from the stack. The int R and software interrupts are controlled using the interrupt flag in the flag register. By setting or clearing the flag, the interrupts are enabled or disabled respectively. The 8086 has instructions to set and clear the interrupt flag. The debug interrupt is controlled using the trap flag. By setting or clearing the flag, the debug trap is enabled or disabled. Exceptions and the non-maskable interrupt cannot be disabled. This means that the 8086 will always respond to them. I recommend that you do this question from chapter 6 programming questions before you proceed to the next lecture.